All right, welcome to section 2.3. We're going to talk about limits today, and that was a song by the Eagles called Take It to the Limit, a song that is much, much older than you and I, okay, but still a classic. We're going to start off today talking about what a continuous function is, and then relate it to what a discontinuous function is, and finally bring in this idea of a limit. So a continuous function, I think, is a pretty easy idea. Okay, a continuous function is a function, literally, that has no breaks or gaps in its graph. So you can easily draw this graph, a continuous function, without lifting your pencil. Okay, that's pretty simple, but this definition of a continuous function is not the mathematical definition of a continuous function. So by the end of this lesson, we're going to talk about the actual mathematical definition of what this is. This is basically my definition to help you understand it, okay? So, excuse me, if this was a definition of a continuous function, then if a function is discontinuous, that must mean it has some type of break or gap in it, meaning you gotta lift up your pencil in order to draw this graph. So we have two different types of discontinuous graphs. They can be what's called a removable discontinuity, meaning that there's some type of piece actually taken away, or you might have a non-removable. So these are the kind of the special cases over here. So if we take a look at these two graphs, notice how they're very, very similar, just a tiny bit different. This one has an extra value above it, but these two are an example of a removable discontinuity. So if you take a look at it, notice how if I were to draw this with my pencil, I would draw right here, but I'd have to literally pick my pencil up, move it over to the other side of this open dot, and continue to draw it. Okay, so I had to pick up my pencil because remember, if you have an open circle, that means you cannot touch it. So I cannot put my pencil there. Same thing going on here. I can draw my pencil. I need to literally pick it up in order to draw this dot, and then I need to pick it up again to continue over here. So these are discontinuous graphs because I need to pick up my pencil. They're specifically called removable because they have some type of hole in them. Notice how it looks like a regular parabola. Okay, we have that U shape. This time it's just upside down, but it looks like a normal graph. There's just a hole removed from it. So there was a piece taken away. So in both of these cases, we would say there is a removable discontinuity at x equals -4 because at this value right here, okay, in both of these cases, that's where the discontinuity occurs. That is the place where I need to pick up my pencil and move it to someplace else. That is the point where that hole is located. Now in these two cases, these are non-removable, so we don't actually have a hole. I know it looks like we have one here, but this one's something just a little bit more different. It's a little bit more special. So the first type of non-removable discontinuity is what we would call a non-removable infinite discontinuity. And if you take a look at this, the infinite is coming from this gap caused by an asymptote. Notice how this piece continues going up, but it's never ever going to go right, and this piece is going to continue going up, but it's never going to go left. So we have some type of asymptote happening right here, and asymptotes are always the infinite case because they go infinitely up and infinitely down. Sometimes we'll have a horizontal one that goes infinitely right and infinitely left. So whenever you have an asymptote, you have some type of non-removable infinite discontinuity. And we're specifically saying it's at x equals 0 because that's where the asymptote occurs, right there on that y-axis. Now this one down here is a little bit different. Okay, you can kind of notice it by the graph, but this one we would say is a non-removable jump discontinuity. So if you can imagine drawing this one with your pencil, okay, and then you got to lift it up, you jump to another value on that same x point. Okay, so this point right here we're specifically talking about is x equals 3. So I need to draw my graph, pick it up, but move it somewhere else on that particular line, on that particular x value. So I stop right here and I jump somewhere else right here and continue my graph. So this one we have a jump motion going on where we have the two dots. Sometimes they might both be open, sometimes they might both be closed, sometimes you might have one of each like we do in this case, but they are found on the same x value because you're jumping from one to the next. So we have three different types of discontinuities. We can have the removable, which is a hole, we can have the infinite, which is an asymptote, or we can have the jump, which is literally jumping between 2 points on the same x value. Alright, so taking those three different types of discontinuities into play, I want you to try to identify the different discontinuities happening in this graph and their x values, and then just describe them as removable or non-removable. Okay, I'll be back in a second to see how you do. Alright, so let's see how we did. If we take a look at the graph, the first one I kind of noticed right here is a jump discontinuity, and more specifically that would be a non-removable. So we can say non-remove, I might abbreviate a little bit, non-removable jump discontinuity at, and the specific x value where that occurs is -3. Okay. Now there actually is another one. I don't know if we found this one or not because it's a little bit more difficult, but we have a hole right here. Notice how this piece is resembling a line. Okay, this piece is a normal graph, but we have a hole in it. There's a chunk missing. That specific type is a removable discontinuity. Little hole there. Discontinuity. And that x value is at 1. So we have x equals 1. So hopefully you guys did really good on that one. Alright, so now it's time to take it to the limit. A big definition going on right here. Okay, lots to write down. A limit, okay, more specifically a one-sided limit, is the y value that a function approaches from either the left or the right. So we're going to be traveling along this graph either from the left-hand side or the right-hand side, and of a given x value. So we're focusing on an x value specifically, but we're trying to find the y value that our graph approaches. So that's a one-sided limit. We can either go from the left or to the right. But the overall limit, okay, just a limit in general, is the same y value that a function approaches at a given x value if the left-hand side, so if this left-hand sided limit is actually equal to the right-hand side. So if we get the same answer from the one-sided limit, if we go from the left and the right and get the same answer, then that specific answer, that specific y value, is the overall limit of the function. So these can be a little bit tricky because we might get one answer from the left, which is different from the right. We might get an answer on the right, and we might not even get an answer on the left. A few different things can actually happen here. So we're going to focus on these different examples, and I'm going to try to zoom in here. Okay, bear with me for a second. And we'll move this and that. Alright, so let's focus on these first two examples. We want to find the limit as x approaches -3 of this function. Okay, so here's our -3 value. I know it's a little blurry on our screen right now, but hopefully it's a little bit better on yours. Here's our -3. Okay, now if we look at this, we want to, the limit, remember the overall limit is if we approach it from the left and the right and we get the same answer. So if we look at this value of -3, as we approach that value from the left, it looks like we're reaching a y value of 4. Remember, we're specifically focusing on a y value. Now, as we approach it from the right, we get the same y value. Notice how if we go from the left and to the right, we're approaching the same y value, and that specifically is 4. Now the difference between a limit is that we're not actually reaching the value of -3. We're only approaching it from the left and the right. So maybe we're getting really close on this side, we're getting really close on this one, but we're not actually touching -3. If we were to touch -3, that's where the function notation comes into play, because this is telling us when we actually put in -3 into our equation, what is the y value we get. So if we actually want to touch -3, we can look at that specific spot right here, and that's the same value of 4. Okay, so remember, the limit is when you approach it from the left and to the right. You want to see what are you getting near to, what are you approaching. We're approaching that y value of 4. If you actually want to touch the value, that's what the point that you want to focus on the actual graph. I think this one's going to make it a little bit more visual for us to kind of understand. Again, we're looking at the same x value of -3. Okay, so that's right here. And as we approach it from the left, okay, we're going to get really, really close, but we're not going to touch it. We're still getting very close to that same value of 4. Again, if we approach it from the right, okay, we're getting very, very close to the same value of 4. So if we get an answer of 4 from the left and 4 from the right, that would be our limit. But notice that the moment we actually want to touch -3, the moment we actually want to see where is that place on our graph, we do not have a spot there. Okay, this is an example of a removable discontinuity. We have that hole. So even though the limit has an answer, okay, the limit actually exists, as we would say, we have an answer of 4, the value itself does not exist. So we would say DNE, if you want to abbreviate it, does not exist because we do not have a specific piece of that graph right there. It's missing. Let's check out the next two. Okay, very similar here. Okay, we're still approaching the same x value at -3, and we're going to approach it from the left and approach it from the right and see what we get. So if we approach it from the left, we get this very, very close answer of 4. Same thing going on at the right. Okay, we're approaching the same value, so the values are equal. That's our limit. But this time, when we actually want to count that answer of -3, we have a spot or an answer down here at -2. So this time we have this almost a jump discontinuity happening, probably, because we have this piece, we got to jump down, and then we got to jump back. So I would say this is a combination of a jump and a removable. It's a removable because we have this hole up here and it looks like a regular graph, but we need to jump somewhere down because we're filling in that spot. So even though this piece is empty on our normal looking graph, we actually do have a value for this -3 input, and that value is -2. We have a point down here. Going on over here, different shape of a graph, we're still reaching that same x value of -3. As we approach it from the left side, we are approaching this value of 4. But as we approach it from the right side, we are approaching this value of -2. Okay, now this time our answers are not the same. So our limit, we would say, does not exist. Because in order for our limit to exist, our answers have to be the same. This one was 4, this one was -2. Those are not the same, they're not reaching the same point, so our limit does not exist. But the moment we want to actually plug in -3, see where that is on our function, we can touch this value of -2. We cannot touch that value of 4. So we would say this would be -2. All right, let's see if I can sneak this last one in here. There we go. Okay, so last but not least, still focusing on -3 right here. As we approach, remember we're looking at the limit. As we approach it from the left, we're reaching this value of 4. As we approach it from the right, we're reaching this value of -2. Those are not the same, so we can say does not exist. But the moment we want to actually touch that value, we want to include it. -3, we get out an answer of 1. This is the only spot my graph actually can touch because these two are open circles. So this would give us a value of 1. Alright, so let's take a look at a different type of graph than the other ones we just did and just review a little bit more about these limits. We're going to focus a little bit more this time on the different sides. So if you take a look at part A, we have the limit, and we want to see as x goes to or approaches -2, and you guys kind of see this little negative sign right there, almost in the exponent position. That little negative is telling you you want to focus on the limit from the left-hand side, because normally if you think about a graph, on the left-hand side we have these negatives. So we're only specifically focusing on the left-handed limit right here. We don't have to worry about the right. We don't have to worry about if the left and right are equal or not. We're just focusing on the left-handed limit. So if we look at our graph, we want to specifically find -2, so that's right there. And we want to see what is the limit as we approach from the left. So if this is our value we're focusing on, we're going to go to the left-hand side. And as we approach this -2, notice how I'm going from -6 to -5 all the way to -2. What does it seem to reach? So here's my -2 value. And what is it approaching as I reach it? Well, the y value looks like a value of 1. So the left-handed limit would be 1. Now, part B, very similarly, we have the limit as x approaches -2, just like we had over here, but this time we have a positive symbol almost in that little exponent position, and that's referring to the right-handed limit. So again, we don't have to worry about the left, we don't have to worry about if they're equal or not, we're just going to focus on the right-hand side. So here's our little -2, maybe we'll draw a little dotted line to help us focus on that. And we're going to focus on the right-hand side of this value. So we're going to approach it like this, and what does it seem to reach? Well, this specific spot right here looks like it's reaching a value of -2. Remember, it doesn't matter if we actually touch -2, we're only approaching it. So it looks like it's getting closer to a y value of -2. Now this is where the overall definition of a limit comes into play, because our part C over here is just asking for the overall limit. What is the limit as x approaches -2? Well, notice on the left-hand side limit we approached 1. Okay, so here's our -2. We approached 1 from the left. And over here, we approached -2 on the right. So the overall limit, since both of our answers are different, would be does not exist. And we can actually see that on the graph because the limit is not reaching the same point. As we reach -2 over here, we have a placement up top. As we reach -2 over here, we have a placement down below. They're not reaching the same point. So the limit does not exist. If we go on to part D, we want the limit as x approaches 1. So if this is an overall limit, we want to check the left and the right-hand side. So here's our value of 1, okay? And if we approach the value from the left, looks like we're reaching right there. And if we approach from the right, it looks like we reach right there as well. Okay, so our overall limit would be 1. Because we get an answer of 1 from the left and 1 from the right. Again, it doesn't matter if we actually touch it, we're just approaching it. Let's check 0. So 0 is right here. Maybe we'll draw a little dotted line. As we approach from the left, it looks like we reach an answer of 2. And as we approach from the right, it looks like we reach an answer, or sorry, -2. Okay, -2. So both answers are the same, left and the right. We have our overall limit. Part F is telling us that we want to approach +3, but only on the left-hand side. Okay, so here's my +3. I want to approach it just from the left, and as I get closer, it looks like I reach a y value of 5. If we go on to part G, I want to take a look at -1. It's an overall limit. We don't have that little negative or plus sign in the little exponent spot, so it's an overall limit. As I approach from the left, it looks like I reach a value of -3, and as I approach from the right, it looks like I reach another value of -3. So there we go. All right, part H, we want to approach -3 right there, and as I go from the left, because it's an overall limit, there's no plus or minus, as I approach from the left, okay, I get close to an x or a y value of 0. As I approach from the right, I get the same y value of 0. So we got 0. Alright, part I. Notice how we don't have the little limit notation in there? This time we're actually focusing on the value itself. So if I were to put in -2, okay, into our function, we would get a value out on our graph somewhere, hopefully, and we need to find it. Okay, so at -2, notice how I have 2 of these spots, but I can only touch the closed one, because the closed means I can actually equal it or touch it. So if I were to put in -2, I would get out a y value of 1. Okay, we cannot touch open circles. If we try f of 1, very similarly, okay, I have two spots over here, an open one and a closed one. Again, we can only touch the closed one, so that would give us a y value of -2. Alright, so I want you to pause the video and try this one. Okay, there's just true or false statements. I want you to tell me, did I actually find these limits correctly? Do I actually get an answer of 1? Does it not exist? These last few ones might be a little bit tricky. Does this limit equal this one? Alright, so pause the video, see how you do, and then we'll go over them in a second. Alright, so let's check out and see how you do. Okay, for the first one, we want to approach the limit of -1, okay, but more specifically the right-hand side. So as we travel on the right-hand side, it looks like we're approaching a y value of 1, which is what they tell us, so that would be true. Alright, going on to the next one, we are having the limit as x approaches 2 this time. And remember, this is the overall limit. We don't have that plus or minus, so we got to check the left-hand side and the right-hand side. Both of them look like they're approaching a y value of 2 because it's kind of constant, it's level, so that one would be true as well. If we go on to part C, we want the limit as x approaches 1 just from the left-hand side, so we're going to come up this way, and it looks like it's approaching that y value of 1, so that one would be true too. So far, so good. Part D, we want the limit as x approaches 1 from the right-hand side. Okay, so the right-hand side would be this piece over here. Drawing this dotted line might help sometimes because you can separate the left from the right. So as we approach it from the right-hand side, it looks like we're reaching this y value of 2. So that would be true as well. Now we have the limit as x approaches 1, meaning from the left and the right, we got to check both of them, does not exist. Well, we actually kind of already found that because we approached 1 from the left and got 1, and we said it was true. And we approached 1 from the right and said it was 2, which we also said was true. So if the left-hand side is 1 and the right-hand side is 2, that means that it does not exist because they're not the same value. So that statement would be true as well. Alright, let's check out 0. 0 right here, we want to approach it from the left-hand side. So as we approach it from the left, it looks like it's reaching a y value of 0. As we approach it from the right, it looks like we're reaching a y value of 0 as well. If the left-hand side is 0 and the right-hand side is 0, they are equal to each other, just like our statement's trying to tell us, so that one would be true as well. Alright. Let's check out the last one. We have the limit as x approaches 2. Okay, so we want to check it out from the left-hand side and the right-hand side. Well, we actually already did that. Okay, up here, we said that the limit as x approaches 2 was actually equal to 2, because from the left, it reached a y value of 2. From the right, it reached a y value of 2. So if we actually got an answer from the left and the right that matched, that means it has a limit. The limit actually does exist. It does not exist, does not exist, I guess. So this one would be false because we actually have an answer from the left and the right that match. So I hope you guys did really well on that. Alright, last but not least, we're going to finally talk about the actual formal mathematical definition of a continuous function. Remember at the very beginning we said a continuous function was a graph that you can draw without lifting up your pencil. And if you were to take a look at this one down here, I could do that. Okay, I can actually trace this on here without lifting up my pencil. So this is an example of a continuous function. But mathematically, okay, we're going to be a little bit more specific. In order for a function to be continuous, it has to meet these three conditions. If it doesn't meet just one of them, then it's discontinuous. There's either that hole there, or there's an asymptote, or there's this jump happening. So all three of these must work in order for it to be a continuous function. The first one is that we have some x value, okay, we normally use c, meaning a constant, or in other words, an x value, that's defined. So in other words, the c is in the domain or it works. So maybe we'll just say, just as an example in this case, that our c value or x value is 1. All right, so down here I have f of 1. Okay, this is my x value, and if I want to try to find f of 1, I actually get out an answer. I get a y value of 1. So notice how the c value of 1 exists. It works. I actually get out an answer. It's found on my graph. So this particular piece, or this graph so far, follows this definition or this condition, okay? Now going on to the next one, the limit from the left and right of c approach the same value, or in other words, the limit exists. So if we were to actually write that out, the limit as x approaches, or in other words, c approaches 1 of our function, it actually has to exist. So if we approach 1 from the left, okay, notice how we get an answer of 1. If we approach it from the right, okay, we get that same answer of 1. The left-hand side and the right-hand side have the same answer, so it meets this second condition. Now the third one is kind of the kicker, okay? The limit as x approaches c, this answer right here, has the same y value as f of c, the same one we had down here. So notice how those two exist, those two match. So this would be the definition of a continuous function. So the actual point exists, the limit itself exists from the left and the right, and the answer from those two pieces match. Now, you can pick what any x value you want. We could have picked 2, we could have picked 3, we could have picked 2.5, but in either case, these three conditions would have been met in any of those cases. So a continuous function, all three of these happen, or they work, for every single x value you can think of. Any decimal, any fraction, any whole number, any negative number, all three of these work for every single x value. So we just used 1 in this case, but I think that this was a very good visual for us to help us understand the formal definition. I might ask you to remember this, or to at least be familiar with it, but in general, I just want you to know that a continuous function can be drawn without lifting up your pencil. Okay, it's smooth, there's no holes, there's no gaps, you don't have any of those jump or asymptotes happening, okay, but just be familiar with that the formal definition involves this idea of a limit that we were looking at in this lesson, all right? So good luck on the practice, good luck on the mastery check, good luck on the application, good luck on everything. You guys do great, you guys always do great, and I'll see you next class.